So if we take a look at this particle Q, that's at spot A, it's eventually going to go to spot B. Now, whether it takes this pathway that's being shown right here, or it takes a pathway like this, or if it takes a pathway like this or like this, it doesn't matter. They're all independent of the path taken. What really matters is the change between the two spots. So if we know that voltage is equal to delta E over Q, if we're trying to find the difference in energies between these two spots, what we're going to be looking at is we're going to be looking at the charge times the voltage at spot B, subtract the charge of the voltage at spot A. Because we're moving, it's going from A to B, it's going to be either gaining energy or losing energy. So in this particular case, Q is the common factor between both of these, so really we could write this as being delta V. So now let's continue to look at a few more things from grade 11. We remember from the energy unit that work by definition is a change in energy, and that was equal to force times distance. Now, I'm not going to use distance in this case because that's not what we've been using this course. We have been using variable r to describe the distance between two objects. Now, we also know that electric field is equal to force divided by Q. So I could rearrange these and say the electric field times Q is equal to force. So if I take this and plug this in, what I'll end up with is Q E times R. And this, by definition, is my change in energy. But we've also said that change of energy is equal to these things here. So really, I could write Q delta V is equal to Q E R. And we can see right now that what we have to do is cancel these two things out. So if we rearrange, we can describe the electric field as being equal to a change in voltage over distance.